Physical chemistry, focus. We will apply the Eyring analysis to a temperature-dependent rate constant, K of T, and then quantify the significance of quantum tunneling using the Wigner correction. Our goals are 1. Build and interpret an Eyring plot, and 2. Compute the Wigner correction and judge its size. The transition state theory rate constant is K of T equals K sub Bt over H times the exponential of delta S double dagger over R times the exponential of negative delta H double dagger over RT. If we take the natural log of K divided by T, we get a line in 1 over T with slope negative delta H double dagger over R and intercept log of K sub B over H plus delta S double dagger over R. Let's build the Eyring plot. On the horizontal axis, we place 1 over T in Kelvin to the minus 1. On the vertical axis, we place natural log of K over T. We plot our data points. We draw the best fit straight line. From the slope and intercept, we extract delta H double dagger and delta S double dagger. Numerically, we obtain the activation enthalpy and activation entropy from the fit. We will present delta H double dagger in kilojoules per mole and delta S double dagger in joules per mole per Kelvin. Quantum tunneling lets reactants cross a narrow barrier even when classical energy is insufficient. The Wigner correction gives a simple multiplicative factor kappa of T to boost the classical transition state rate. The Wigner expression is kappa of T equals 1 plus 1 over 24 times the quantity h bar omega double dagger over K sub Bt squared. Here, omega double dagger is the imaginary barrier curvature magnitude in radians per second. Let's quantify the size of tunneling. We plot kappa of T versus temperature for a barrier curvature corresponding to 1,000 inverse centimeters. The correction decreases with increasing temperature. At 300 Kelvin it is large, and by 500 to 600 Kelvin it is smaller, but still non-negligible. How does this change the rate constant? The corrected rate is K corrected equals kappa times K transition state. At 300 Kelvin, we multiply the classical Eyring rate by the Wigner kappa, which we found to be close to 2. So tunneling nearly doubles the rate at room temperature for this barrier curvature. Statistically, the Eyring plot is a linear regression. The slope maps to delta H double dagger, and the intercept maps to delta S double dagger. If you propagate uncertainties from the fit, you obtain confidence intervals on these thermodynamic parameters. More temperatures and wider temperature span reduce parameter correlation and yield tighter confidence bounds. Let's summarize the workflow. First, measure K of T experimentally or compute it. Second, build the Eyring plot and fit the line. Third, extract delta H double dagger and delta S double dagger. Fourth, estimate tunneling with the Wigner factor. Finally, decide whether to report K corrected or the classical rate, depending on the magnitude of kappa. Caution! The Wigner formula assumes a parabolic barrier top and small to moderate tunneling. For very light particles or very low temperatures, more sophisticated tunneling models may be needed, such as Eckhart barriers or semi-classical instanton approaches. But as a quick correction, Wigner is simple and often informative.